Okay, I want to clear up something that I didn't make very clear in the drawings, and that is about oxygen being the final electron acceptor. Yep. Okay, I realized I was missing something that might be very important and confusing to some people. So let me open up a new one. So I just want to go over something very quickly. So this will be a quick review also. Okay, so we know that glycolysis occurs in the cytoplasm, and the main point of that is to break down glucose into 2-pyruvate, right? So if there's no oxygen in an animal cell, that pyruvate will be converted to lactic acid, and in the process, we're going to regenerate NAD+, which will help glycolysis go, right? And in the process of glycolysis, we get out 4-NADH, and we get out 2-ATP, right? If there is oxygen, this pyruvate is going to go into the mitochondrial matrix, right? So that pyruvate is going to get broken down into acetyl-CoA, right? And in that process, we're going to get rid of carbon dioxide, and we are going to make NADH, right? In the Krebs cycle, this acetyl-CoA is going to be converted to a 4-carbon molecule. Don't have to know the details of that, but what we're going to get out of the Krebs, and here I'll show it going out of the Krebs, we're going to get 3 carbon dioxide, right? And that's going to go times 2. We're going to get 1 ATP, but that's going to be times 2, 4 NADH times 2, and 1 FADH2 times 2, right? And I just realized that this guy down here, the net is going to be 2 NADH for glycolysis, right? So we're going to get all those things out of the Krebs. And then these two molecules, from Krebs cycle and from glycolysis, are all going to feed into the electron transport chain, right? And that's some molecule or some proteins or enzymes on the intermembrane, the cristae of the mitochondria. And as those electrons from NADH and FADH2, so those are going to become oxidized, right? And as those are oxidized, the electrons are going to be moving through this chain. And as they move through the chain, their final electron acceptor is going to be oxygen. And I'm going to explain that. So sorry, I'm going to do that in a second. So as we do this, hydrogen is going to be pumped in, right? Filling up the intermembrane space with an electrochemical gradient. We then have a little ATP synthase where these H's are going to go flow back down. And in that process, we're going to make ATP, right? The part I really want to talk about is this final electron acceptor, which is oxygen. All right, so oxygen, which comes as a gas, O2, ooh, I don't really love that, okay, is the final electron acceptor, right, in the ETC. And it's a little bit like a pipeline, right? If you block up the end of a manufacturing chain, then everything in front of it stops, right? So, so that's really important to think about. So oxygen is really important for the synthesis of ATP because it allows this process to kind of flow. So what we have are 2 electrons coming out of the ETC, right? Those are going to join with 2 protons that are building up in that electron or in the intermembrane space. And they are going to go with half of an oxygen. And when I mean half of an oxygen, remember oxygen is diatomic, right? So there's 2 of them. So half an oxygen just means 1 oxygen atom, right? If we have 2 protons, we're dealing with 2 H atoms, right? The electrons are from either NADH or FADH2, right? And when these come together, they form water, right? So we have one oxygen atom from our half oxygen. We have our two H's from our protons, but to make those H's full hydrogens, they need those two electrons, right? So this is that final equation, which is responsible for making water. And so here, I'll use my space. Hopefully that'll get out of the way, right? So we have two electrons from the electron transport chain. We need two protons, and we need half an oxygen, which is one oxygen atom. And that will make our water, which is one of the outputs of cellular respiration. All right, hopefully that will clear some things up for you. And that's kind of just a very basic overview of cellular respiration. But in particular, I wanted to talk about that oxygen being the final electron acceptor. And one cool thing to think about is that if you disrupt this pathway in any way, for example, if we had an inhibitor that inhibited ATP synthase, for example, what would build up and why? Right? So what would build up is would have a really intense hydrogen or proton gradient, but you would not make very much ATP, right? So if we, for example, got rid of the final electron acceptor, then NADH would build up because it couldn't be oxidized. FADH2 would build up because it couldn't be oxidized, because this whole pathway would kind of build up, right? So you guys should be able to think about what happens to each of these pathways if you have an inhibitor or a poison. All right, thanks.